Hi everyone, hope you're doing well. Let us continue the previous lecture on numerical aspects in quantum mechanics, and this time we will discuss time evolution or propagators. All right, same ideas can be used to solve any equation. For instance, optics, the paraxial approximation. You just replace time t here by some distance z, and here the Hamiltonian is another matrix. But here we are concerned about quantum mechanics, and it's a very important aspect of quantum mechanics that the evolution operators in quantum mechanics, or the propagators, in the sense of propagating the solution forward, they are unitary. All right. This means that at any given instant of time, the state is normalized to one in this problem in quantum mechanics, but it can be to any value. But your evolution operator must be unitary. So it's a very strong test for your algorithm, because if your eigen, or sorry, your ket or your state is changing length, is changing size, be sure your algorithm is doing something wrong. So this is a very important test. You can at each step just see if your solution is normalized to unity. In quantum mechanics, is what is relevant. All right. So in the previous lecture, we discussed finding the eigenvalues for Hamiltonians. In this case, suppose that you are trying to calculate the evolution of a state which is not an eigenstate of the Hamiltonian. So your psi naught is some psi at time t equals to 0 is not some eigenket of your Hamiltonian. And eventually your Hamiltonian is time evolving also. So the problem of finding eigenkets is no longer, it, it doesn't make much sense anymore. All right, so this is the problem. We are trying to, given the initial condition, find out what happens numerically to the function at some time. All right. So let us do this by one method. There are a lot of methods to do that, and your Hamiltonian can be the Hamiltonian of your previous problem. So now your function is not a function of just position, but position and time, but it can be a simpler Hamiltonian here. It can be a spin Hamiltonian or anything you wanted to find out how it evolves in time. All right. So what we can do here, we just multiply everything by dt. So we have the differential of the state here, which is a vector from general arguments. It's a vector, and we multiply this h bar, 1 over h bar, both sides, and by minus I, so to eliminate this factor from here. So we have minus I h bar, the Hamiltonian, times the function psi of t. All right, this Hamiltonian here is evaluated at some time t. All right, and dt, we multiply that. But now look that we can integrate both sides of this equation. We just multiplied everything by dt and divided by I h bar. That's what has been done so far. All right, now we can integrate both sides. All right, if you integrate in any given limit that you want, you'll have a problem. So for instance, if you consider it as the inferior limit to be the time t equals to 0, and you integrate to time t and this interval is not infinitesimal, you don't know what happens there. But if you consider now some time t, now you insert here some t prime just to change variable because you want to write the results as a function of t. So the intervals you call t, and you integrate some interval from t to t plus some delta t. This is infinitesimal in a mathematical sense, both sides. Change variables here to t prime, all right? Because you need to replace limits in the end. You'll find out the following. Well, the left-hand side is exact because when you integrate something, the differential of something, you have that something evaluated at the limits. So here you have psi of t plus delta t, which is a vector, by the way, this is a vector, right? Minus the psi at time t, right? This is the left-hand side, is equal to that integral. And now you can approximate it numerically if delta t is small. How small? You need to see the convergence. You need to see that states, any initial state stays normalized in the future. All right. So if your delta t is good enough, is small enough, your evolution operator here, the solution, the numerical solution of this equation will produce normalized states, normalized to 1 at each step in time. All right. So this delta t is small. How small? You need to test it in your real problem, right? Given the Hamiltonian. But of course, if the Hamiltonian has some time varying parts, this delta t must be sufficiently small to capture or sample correctly the time variations of the Hamiltonian, all right? But now we have to integrate the right-hand side. And you can integrate just considering, okay, I will consider that this is a constant over this interval, and I will replace this by the function evaluated at time t times delta t, the interval, all right? This is a first order explicit method. Or you can do a second order method, which we will employ here, but will be implicit. And you can use Simpson's method for integration or Runge-Kutta for whatever. But we will consider the simplest and very robust, very convergent method, which is to consider the trapezoidal method here. So to calculate the area, because integral is an area, okay, you have a function of this form here, some function in the integral, in the integrand f of t, suppose some x, I will change variable here just to make it easy. So some f of x from some x to x plus delta x. I have 2 points here, the function here and the function here. Okay, I want to calculate this area. All right, what can we do? I have the function of x plus delta x here. I have the function of x here, and we use a trapezoid whose area is just, when you have something like this, right? What is the area of something like this? Suppose this is B, this is A, and this is your delta x. This is the function evaluated at x plus delta x. This is the function evaluated at x. The integral, the result of the integral is just A plus B is the sum of the sides times the width, which is delta x, divided by 2, right? This is the area of this object here. And in this case, we do that. We just plug in here the Hamiltonian calculated at some later time times the function evaluated at a later time, which as a matter of fact is what we are trying to calculate, right? We are trying to calculate this thing. Okay, plus the Hamiltonian at time t, the function of time at time t, right? And this thing here is the function evaluated at here, and the other is the function evaluated at here. We need to divide it by 2, and we need to multiply by the interval, which is just delta t. All right, so delta t. I guess you can see what we written, but I will read this. I will write this function again, right? So what we have, what what we have is the function we want to calculate is appearing in the left hand side and in the right hand side, and we need to put them together. We'll pass it to the left hand side, and this, which is already known, supposedly we already know the function at time t. I will put it to the right hand side, and in this way we will have the identity matrix, because I can plug in an identity here, I can plug in another identity here. So the identity matrix, and when we bring it to the left hand side, we will have plus, because this minus becomes plus I, the Hamiltonian evaluated at time t plus delta t, divided by 2 h bar, twice the h bar, and times delta t, right? And this multiplies the function evaluated at some later instant, which is equal to, when you bring that to the right hand side, this factor here, we will find out the identity here, and minus I delta t divided by twice the h bar, the Hamiltonian evaluated at time t, times the state at the initial time, or the time t, which is supposedly we know what it is. Okay, so it's a recursive method. It's a propagating method where we start with the function at time t equal to 0, and we calculate the function at time t equals to delta t. And then we have the function at delta t. We calculate at twice the delta t, and so on and so forth. So this is numerical method. But this is implicit because the Hamiltonian appears here and appears there. So we need to get rid of this term here, and we need to multiply, therefore, by the inverse matrix, both sides. Inverse of this factor here, notice this is different from that, because here we have a minus, here we have a plus sign. And in this way, we will find out that psi evaluated at t plus delta t corresponds to something like this. A unitary operator which brings the function from time t to t plus delta t, right? It evolves the function from t to t plus delta t, and it is applied to the function psi of t, right? And this thing here, which is the propagator or the evolution operator, is given where we have this operator is given by the following. This matrix inverse, which is sometimes difficult to calculate. These are the imaginary, the H bar, the 2, the delta t are just numerical factors. The matrix is in the Hamiltonian, evaluated at the time t plus delta t, right? We need to pick the inverse matrix. So we multiply here, the matrix times the inverse matrix gets 1. So therefore we eliminated this factor from the left-hand side. And now the evolution operator is this thing inverse times this thing here, 1 minus I delta t divided by twice the h bar and the Hamiltonian evaluated at time t, right? Suppose the Hamiltonian is time independent. If the Hamiltonian is time independent, but your initial state is not an eigenstate of the Hamiltonian, this thing here can be calculated only one time, all right? Because if this is not time dependent, this is not time dependent, the evolution operator just propagates from some time t to t plus delta t, but it's a constant matrix, all right? It produces the evolution by an infinitesimal amount of time, all right? So it brings the function from time t to t plus delta t. So how do we perform numerical calculations, all right? You need to define properly things in the computer. So if you're using a numerical solver, I will just sketch what would look like a numerical propagator. So numerical propagator. If you're using something like MATLAB, you need to clear variables. All right. So you need to define a part where you define constants, where you define variables, and define the time, define the space of computation, of course, or of numerical calculation. So you need to set some t equals to lin space from some initial to suppose 0 to final time of computations. With the given nt, you calculate the delta t, which is the second minus the first, and it's equal for any two sets of points, all right? You need to define if your problem is a problem depending on space, you need to define x as a line space, a lin space from some initial to some final with some endpoints, all right? If necessary, but if it's not necessary, okay, all right? Your Hamiltonian can be a spin half Hamiltonian, so this is not needed, right? And you just need to define the polymatrices in your computer. So if you need to define polymatrix in MATLAB, suppose sigma x, you can write this the following way. This bracket 0 1 semicolon 1 0. MATLAB understands that this is the first row, this is the second row, but you need to insert this comma, the semicolon here, because if not semicolon, it will write the row vector, right? So you need to define matrix. And you can do it for Sy and Sz. You can multiply by constants here, all right? I'll not waste some time here defining things. But suppose you have defined all your constants, your variables, your space of calculations, the delta t here, you have the h bar, you have mass, you have charge, you have Bohr magnet on magnetic fields, functions of time, because you next step you define, for instance, you define it time, you define it here the number of points, the final time, you define the initial position, the final if necessary, you define everything here, all right? All the constants are defined, all the space is defined. Now suppose you have to define some magnetic field, which is a function of time. You need to insert a function here, which is the function defined in magnetic field. It is a vector, right? You need, well, just format your Hamiltonian the proper way, right? This is what you need to do. And now, suppose you have an initial function, so you need to define the initial function psi 0, the initial state. I'll write it psi 0, all right? In computers, eventually you are not able to use the Greek letters, so psi 0 is equal to some state here you need to define. It can be a function. For instance, if you are trying to calculate the evolution of a Gaussian wavepacket in problem with space, it can be defined as the exponential of minus some x squared divided by some x naught squared, which is the length of the Gaussian, or whatever. It can be spin or spin. It can be, suppose, spin a state which has in the z component 1 and 0, so it's an eigenstate of spin in the z direction. But you can have an Hamiltonian which depends on time, so this spin will precess and anything can happen there. So your psi here, your initial function is just the two-component vector, is a Pauli spinor, all right? You define what is your initial state, what is your initial vector. And then you'll have a form, all right? A for, which is a loop, all right? So till you find n, for suppose n equals to 1 until you get the n t points in time, or for t, suppose for t, you will run all the time here. You will run from the first to the last time for t. I don't know how and what software you use to implement this algorithm, but of course you will calculate the evolution operator. Okay, here they are matrices. Of course, you will need to define an identity here, which is the I matrix of yours, not the time. It's not the time, it's space here, or spin, if spin dimension 2, which means the dimension of the Hamiltonian, dim of Hamiltonian here. This the dimension of the Hamiltonian, this identity matrix. Right, so this will be the inverse matrix of this identity minus I times, you need to use the proper language here, the syntactics, of course, the imaginary, for MATLAB, imaginary I is already square root of minus 1. So try to not use this as an index, because I for MATLAB is the square root of minus 1, or J also use it as the square root of minus 1. So Y and J are not good indexing variables. Use another things, but take care that you are not using M, and M was mass, or N, and N is another thing. Try to be precise and try to not confuse your variables, of course, but then you will find out this is plus I times the Hamiltonian times the dt, which you calculated, divided by the h bar, divided by 2, times its matrix multiplication, the identity, minus I times, and this Hamiltonian you need to calculate previously here at time t plus delta t. All right, so let me use some index n here. N equals to 1 until you reach your last point, nt. So this Hamiltonian here, I will call it h1. So h1 is defined as the Hamiltonian at time at the n instant of time plus 1. Of course, this must be properly calculated, all right? And the h2, which will appear here, the h2 times dt divided by the h bar divided by 2 is calculated at time t. So this is a function at the indexing number n, and this index is time. All right, so you find this evolution operator, and then you just find your psi equals to, suppose you write the psi initial here as without this zero or this not here, so you can calculate this way. Psi is equal to the operator multiplying this psi. You need, of course, to take care that vectors are defined as column vectors, matrices are properly defined, but in the end, your algorithm just do the following thing. It calculates u as a function of the n plus 1 and n, right? It calculates this, and it calculates your function, which can be a vector, all right? Calculates your n plus 1 function here, applying this n plus 1 n operator times the previous function. And this will run till you find your last step, till you encounter the last time here. To be precise, this will be running from, I guess, 1 to nt minus 1, because you need to find out the last step. You'll find out here the n plus 1, which is the last time calculation. But of course, these are a problem for defining variables, all right? But that's it. Your propagator, you define your constants, define your spaces, and you just implement this operator here, which corresponds to an Euler method, an implicit method of order 2. So the convergence is as good as the order of delta t squared, I guess, or cubed. All right, but the order of the operator in the end is delta t squared. So your error gets delta t to the cube. So the delta t must be small. So the convergence is achieved for your software. But then you can calculate the steps. You can define your initial state, and this will calculate for you. Or if you want to write it in a different way, you have to define definitions, and then here you'll need to define your psi 0, all right, because it's an initial state. You define your time interval here, time interval, and then you apply to find out the psi 1, the evolution operator between 0 and 1 to the psi 0, and then you apply to find the psi 2, the evolution operator between 2 and 1 to the psi 1, right? And then you do the number of steps till you reach your final n, which is the evolution operator connecting this n to the previous one, the n minus 1. All right, so you reach the final step of your algorithm. You'll keep applying you. So if your evolution operator is a constant in time, you need to calculate it just one time. You don't need to analyze or to upgrade your evolution operator, because if the Hamiltonian is time independent, your problem is properly defined by a time independent evolution operator, right? Which corresponds to calculating something like this, of course. And you can also do that if the Hamiltonian is time independent. Of course, you could do that by exponentiating a matrix. Some softwares like MATLAB can do that. All right. Well, you can apply this to the problem of a Gaussian wave packet and the tunneling problem, which is a rather involved problem if you want to try to solve that analytically, but numerically it's a very easy problem to do. I will recommend this book, Quantum Mechanics by Schiff. It has the solution, a numerical solution. There is an analytical solution for some tunneling problem, but he defines a potential barrier here. I don't know if you can see a potential barrier right here, and he inserts a Gaussian, so the Gaussian moves and it reaches the potential barrier, it gets scattered by the potential barrier, and this evolves in time. All right. So for distinct widths of the Gaussian, the heights of the barrier, you can have distinct results. So if you have this at hand, just take a look at this book, and you can eventually use the Hamiltonian we defined in the previous lecture. You can just define the potential profile to be a barrier, a rectangular barrier, and you can insert a Gaussian wave packet moving to the right, and it reaches your your barrier. Some parts will be reflected, some parts will tunnel through the barrier, and you'll find a very interesting problem to solve numerically, which is corresponding in optics, for instance, to a wave reaching a distinct refractive index region. So it comes from a region with one index of refraction. It its incident at a distinct refraction index region. Parts are reflected, parts are transmitted. It's the analogous problem in quantum mechanics. So a wave packet moves, finds a potential barrier, parts are reflected, parts move, tunnel through the barrier, and it's a very interesting problem. All right. You can find a wave packet moving towards a potential well also. So there will be a probability of that particle to become to go to an eigenstate of that well. So it's just that the particle is collected by the well and becomes trapped inside the well, right? You can do that using some propagator, right? So you have a barrier or a well, right? This is zero energy corresponding to potential energy. This is potential energy. So this is a well. The energy here is mine and it's negative respective to zero. Or if you put zero here, the sides are above zero, and this is a barrier. All right, zero here, some u not there. These are very interesting problems to solve numerically. All right, it's very educative or very interesting problems to solve. Right. but it's a lecture which was intended just to produce some some lateralities to our main course, all right? But it's very instructive for you to do an implementation at the computer, all right? So I'll finish here. I don't think it's much clear, but I don't want to waste a lot of time in numerical simulations and numerical computations. Just an overview of what you can do or what you need to do to produce numerical calculations of a to try to calculate the eigenvalues or to produce a time evolution, and that's it. See you next time.